Hello, welcome. Today let's try to solve another Leetcode problem, 279 perfect squares. So we are given a number n. We need to find how many perfect squares can be summed up to n. So for example, there are 3 perfect squares. We're gonna calculate the least perfect squares. So for example, 4 plus 4 plus 4, it is 12. So for this number, like 2 to the power of 2, it is 4. So this number, this perfect square can be repeated. So if you see this problem, we are given a number 12, and we want to find how many numbers can be summed up to 12. So this is a typical knapsack problem, but for this number 4, it can be repeated. So it is unbounded knapsack problem. Let me first explain my template for the unbounded knapsack problem. So for the basic idea of unbounded knapsack problem. So we are giving a value v and we are giving a weight. So we want to check how many we want to check what is the most values we can get with a limited weight. So this t is the limited total weight. So with this condition, but for each of the items we can get as many as possible. It means each of the items will be repeated. So the basic idea is we're gonna check if this I is for the array index, if this I equal to the length of the array, this is weight. So the v is the value, or the weight, it's the same length. So if it is equal to the value array, it's gonna be return 0. It means we need to stop the DFS. So if this t, if the total is less than 0, so we're gonna return the negative infinity. And here will be the hard part we need to understand. So because we're gonna choose the maximum value we can get, so we're gonna use a max. So this is why if this total is less than 0, it means it is not possible. So we're gonna return a negative infinity. Otherwise, this v and w will be the same. And here, this t is just to start from the total. So this t, if we decided not to choose the current item, so we're gonna choose the next item. That is why t is the same, but I will be plus 1. So if we decided to choose the current item, so the t will be minus the current weight, so it will be minus wi. But this I will be the same because it can be repeated, because this is unbounded knapsack. So this is the basic template. And we also need a case to use the memory. And in this way, the time complexity will be t times I. And this way, w will be the same. Normally, it is inside the description, and we can take it out. Take it out of the template. So normally this is the basic idea for solving the problem. Let me just copy the template, because basically we're gonna change this template, and we need to understand why we can use the template. Unbounded knapsack template to solve the problem. So I need a square array because the maximum number is 10 to the power of 4. So this means I can prepare a square array. I will put it outside of the class, because in this way I don't need to check each of the squares while I enumerate the class and the function. If I take it outside of the class, so it will only execute once, because this square will be a constant array. So I'm gonna prepare a square, and this square will be I times I. So for I in range, I will be starting from 100, because this will be faster for the memorization with search. The DFS with memorization. So if I starting from the biggest number, I can go out of the loop earlier. So for I in range from 100 to 1. So this is a 0 and this is going to be minus 1. Now the hard part will be the DFS. Yeah, so I'm going to use this f function as the DFS function. Basically I need to return this t. For here I'm going to start the t. I'm going to start from 0. It means the target value. Yeah, so the target value will be starting from 0 until this value can become like this n, 12. Yeah, and my index will also be 0. So it will be like this. Now I'm gonna delete this v and w because I don't need it. Yeah, now I'm going to check what is the least items I can get, which some of them will be equal to this number n. Yeah, and so yeah, I'm gonna check the least. I'm gonna check the least items because for this 12, maybe 1 plus 1 plus 1 plus 1, it will be 12 ones. It will be, yeah, it will be bigger combinations. Maybe it is 12 because it will be 12 ones. Yeah, but here it is a 3. It means I have 3 fourths. Yeah, how can I do it like that? So it means from here I basically need the minimum. Yeah, to check all the combinations. Yeah. And here, this f is just for the total from 0. If I decided not to take the item, it will be I plus 1. Yeah. And here, if I decided to take it, it will be the t plus the current weight. Because I'm not going to do it like that. I'm going to do it with the t, the target value starting from 0. And if this t equals to if this t equals to n, I will count it. Otherwise, I will not count it. Yeah. So here will be the I because it is unbounded knapsack. So this I will not plus 1 because for the next iteration, yeah, I'm not sure if I take it or not take it. I have to decide. So if I take it for the next time, maybe I will take it. So here I will not plus 1. Yeah, but I need to plus this result. So here is a value, but I need to count the items. I just need to count the numbers. Yeah, I don't need to plus this value basically. But what I need to do, I need to plus 1 because I've already taken 1 item. Yeah. If I didn't take item, I need to plus nothing because it is a plus 0. But here, if I take 1 item, I need to plus 1. Yeah. Let me delete these areas. Maybe you will see it clear. Yeah, so because we are going to check the minimum, it means I need to return the infinity. Yeah, if I were to return the infinity, I need to check this t. When I need to return this infinity, so the total will be like that. If this t more than the number n, yeah, it means it is impossible. Yeah, so if my total already more than this number 12, maybe like 9 plus 9 is 18, it's more than 12, so I will return an infinity. Because with the minimum of infinity, I will always choose the smallest number, so I will return an infinity. Otherwise, if I equal to the length of the, here will be the squares, yeah, the square array, because I gonna use this array. If it is equal to the squares array, I can return 0 or 1. I can return a 0. It means I've already found it. Yeah, I can return 0 if the t equals to this value n. Else, I'm gonna return infinity. It means I didn't find it. Yeah, because I always check the minimum value. That is why I prepare an infinity. Now let's check what else. Yeah, here is the square. And we also use the cas, and this is the DFS part. Basically, it is the memorization of DP part. Yeah, because we use the DFS with memorization, and yeah, let me just check if there is anything else. Normally, I'm gonna prepare the result as this result equal to this f0 is 0. Yeah, and I'm sure there will always be an answer, because no matter what n is, there will always be an answer. For example, n equals to 12 or 13, there will always be 1 plus 1 plus 1 until to this number. Yeah, so I don't need to check the infinity, because I believe there will always be an answer, because we're gonna check the minimum. Yeah, as you can see from the description, it didn't tell us if you didn't find it, you're gonna return a -1 or any value. It didn't tell us. Yeah, it is because we can always find the answer. Now let me just submit it to tag. Oh yeah, I forgot to change this W. So everything for this W needed to be the square. Yeah, let me check anything else. Yeah, let me run again. As you can see, it works. Yeah, maybe you think this is like a magic. No, it is not, because this is unbounded knapsack problem. We just need to use the DFS memorization to solve the problem. There's no difference from the real DP tabulation, but the tabulation will be much harder. I mean, for each of the time I solve it, maybe I need to use half an hour to analyze all different cases and try to understand it. But by using the DFS plus memorization, maybe I just needed to use 1 or 2 minutes. I can find the idea and maybe 1 or 2 minutes to code it up. Yeah, because this will be easier. But the most important thing is about I need to optimize the DFS with memorization. Otherwise, sometimes you cannot pass. For one thing, you need to optimize like this. So for this total value, if it is more than n, we're gonna stop it immediately, and we're gonna return an infinity. For example, it is 100, but n is 12. It is bigger, so we're gonna stop it. Yeah, and also there's another thing for the square. So inside of the square, it always sorted in decreasing order, because we would always have the bigger number first. Yeah, and then the smaller number. Yeah, now let me just run it and submit it to tag if it works. Yeah. Yeah, it is the memory. As you can see, it is go out of the memory while n equals to 60,000. Yeah, it happens a lot. So we needed to do some trick to fix it. Yeah, we can fix it like this. So because we have the DFS, we have the f function. So f can use cast clear. Because we use the cast, so for each of the time, we need to clear the cast. Why? Yeah, because the cast is too big. That is why we have the memory excited. Yeah, it is not the time excited, it is the memory. So we need to handle the memory. So here we prepare the memory, and after each of the time we get a value, we clear the memory, and then get the result. And for the next testing case, we're gonna repeat it. We prepare the memory and clear the memory. Yeah. Now let me submit it again to check if it works. Yeah, as you can see, this time it works. Yeah, there's no memory excited. Yeah, but you can still see that the memory is, yeah, it consumed so big memory, and the time is much slower. Yeah, because this is the DFS, function calls always takes more time. Yeah, but the time complexity is t times I. So t is, yeah, let me check the t. T is n, because maximum t can be n. And this I is the length of the squares. It is 100. So 100 times 10,000. Yeah, so it is a million. It is 10 to the power of 6. That is why it is slower. Yeah, 10 to the power of 6, 10 to the power of 4 times the length of the square, 10 to the power of 2. Yeah. Thank you for watching.